This is part 2 of the lecture on motors and drives, and we're now talking about engines used in many applications, transportation primarily, but they're also available or used in stationary applications or to drive lawnmowers and like walk-behind tractors and backup electric generators. Anyway, internal combustion engines could be spark ignition engines, auto or clerk, that is 4-stroke or 2 strokes, and then compression ignition engines, diesel engines. There are also hot surface engines, sometimes called semi-diesel engines, and then we have gas turbines used in turboprops and helicopters, in some infantry tanks, because they run on the same fuel as airplanes. And then we have external combustion engines, like steam engines, piston engine type steam engines, the Stirling engines, and steam turbines. This is a review of the equations for power and torque, and you have power defined as work per unit time. In linear motion would be force times displacement over the time it takes to perform that displacement is force times velocity. In rotational motion we have torque, that is force times radius. So it's a rotational motion, again, force times radius, that's torque times omega. Okay, and conversion between kilowatt and or calculated power in kilowatt using torque in newton meters and RPM would be this equation. So you have kilowatt and again newton meters and RPM. So this constant 9,549, it's actually going to be 1 over 1,000 times pi over 30. And if you to convert torque in pound-foot and RPM in RPM, you have this constant 5,252. 1 kilowatt of power is 0.7457, so like 3/4 of a kilowatt is 1 horsepower, and then 1 horsepower is 1.341 kilowatts. Horsepower is an historical unit. Kilowatt is used mainly with electric motors. Increasingly you see engines having their power reported in kilowatts. Since it's a smaller number, consumers like to hear, if you report a power in horsepower, it will be a larger number. So it impresses consumers a bit more than learning their power in kilowatts. Okay, internal combustion piston engines employ slider crank mechanisms, one or more, if it's a single cylinder, just one, to convert the expansion of gases resulting from burning of the fuel mixed with air in the burning chamber. There are engines other than using pistons. There are the Wankel engines, and there are other designs, but this is the most common non-piston engine. It's used in so yeah, there are some automotive applications. NSU was in Mazda, I think they used them. Here to the left is it's shown a side valve, also T-shape, T-chamber shape, I believe it's called, piston engine is the type you've seen in many lawnmowers, 4-stroke engine. And then there are aircraft, including model aircraft engines, that use Wankel design. The problem with Wankels is that yeah, it's simple. It's much better balance. It's just rotating masses, which can be fully balanced. But the problem is with sealing. Okay, there are issues with sealing these tri-lob rotating body relative to the oval chamber. So there's a drawing showing the 4 strokes of an engine, a piston engine. So a spark ignition engine. So there's the intake, there's the compression, ignition and expansion, and burn gases are expel propulsion to the atmosphere. Again, when selecting an engine, you look at the torque speed curves for full throttle and the full load power curve, and there are some other diagrams available to judge their fuel efficiency, the onion diagrams. So generically, you would see, and they are provided on the same graph. So you see the torque curve, and you see the power curve, so the maximum torque, since torque is derivative of power, you will see the maximum torque being associated with the steepest tangent to the power curve. Also provided is the braking torque, so also called thrust characteristic curve. So when you it's good for engine brake analysis. There's some, so we identify the maximum torque, there's a maximum power, there's the torque of maximum power, and the corresponding RPMs. Okay, so RPM with maximum power, RPM with maximum torque, all used in analysis. So we have maximum or nominal power. I said engine power, maximum torque, nominal torque is torque at maximum power, RPM or speed at maximum power, speed at maximum torque. In order to compare engines, we have some parameters that are used in comparisons, and one is torque increase or torque elasticity. So you take the ratio between the maximum torque and the torque at maximum power. And there is also engine speed ratio, or engine elasticity is the ratio between RPM of maximum power and RPM of maximum torque. And we call an engine that has greater elasticity when the product R times lambda is greater. And it means that the engine can provide better output at low and medium engine speeds for transportation applications, like gear changes. We have speed spread. There will be the ratio between maximum and minimum RPM. There's power per liter, as well as kilogram per horsepower, horsepower per kilogram. So a turbocharged engine or a 2-stroke engine may have this number, turbocharged for sure. 2-stroke engine has this number higher. And then diesel engines are heavier because of the higher compression ratios, and their kilogram per horsepower it's higher than for gasoline engines. And extending this to gas turbines. Gas turbines have even better kilogram per horsepower characteristics. For real engines, we can have various various appearances of the torque and speed curve, torque and power curves, that is, as function of engine speed. And again, these are full throttle. You seldomly, or you don't operate an engine full throttle for too long because it can damage its components. But yeah, they could be, you can see flat, rising, this one in buffalo shape, and this is a constant power shape, sometimes influenced by a governor. For example, this is of a what is this, a diesel engine, turbo intercooler. So you see the drop in both power and torque. You have a centrifugal governor that limits the intake of fuel in order not to produce soot, that is to exhaust, to have particulate emissions, carbon black. Okay, so various shapes. I did an experiment once, and I took the torque curve and digitized it, and using the early equations, you can, if you have the power or the torque, you can calculate power, and vice versa. So if you have torque at various speeds, you can calculate power at the same speeds using the early equations. And what I found is that you don't get the curves one from each other, and I was wondering why. Well, this is because these are average curves between experimentally determined for various for different engines of the same type, of the same model. Not two engines are 100% identical, and both the torque curve and the power curve are individually or averages themselves, and it's not expected that the I mean, for a given engine, yes, but if these are average curves, you don't get them as reciprocal using the early equations to get one from the other. Okay, so these full throttle equations could also be accompanied by a consumption curve, again for full throttle. But you don't operate an engine full throttle. If you do, it quickly damages. Maybe an aircraft engine, small aircraft engine, you force it full throttle for a few tenths of a second when you take off, and then when cruising, you reduce it to 60-65%, and it's also for fuel efficiency reasons, as well as extending the life of the engine, not overheating, not overloading the bearings and parts. Okay, so we have what are called engine spread and throttle maps, and you're looking here at partial throttle. So we have the full throttle curve for torque, and full throttle curve for torque for a different engine. This is so one is for spark ignition engine, the other one is a diesel engine. And if you're on a only 30% throttle, of course the maximum torque will be different. And what else? Oh, and we also have different appearance. So for the gasoline engine, they appear to be concentrated, the higher throttle curves, versus being equally spaced for this diesel engine. So different appearances. All right, consumption map. I hinted already, but yeah, this is a for efficient use of engines. You want to be aware of these consumption maps, and consumption could be absolute consumption in grams of fuel per hour, and then we have specific consumption, that is gram per kilowatt hour. Okay, and for a given engine, these number varies with load, but you'd like to maximize the power generated per gram of fuel consumed. Okay, so and everybody knows that diesel engines have higher efficiency than the gasoline engines, and we can go between the absolute fuel consumption and specific fuel consumption by just dividing by the absolute fuel consumption in by the actual power. Okay, so this is a specific fuel consumption. You take the absolute fuel consumption. Let's see, have I absolute? Okay, so could change these to ABS. All right, so and then specific. Yeah. Okay, so now we're fine. So you just divide it. You divide by the actual power and get the relative fuel consumption. And this is how a relative fuel consumption diagram would look like. Move this up to increase the size of this figure to look at it. So there will be lines of constant absolute fuel consumption, but in general, as you increase load, the absolute fuel consumption increases. The relative fuel consumptions, they have different appearance. So there are curves of equal relative fuel consumption. These are the onion diagram maps or graphs, and you can also overlap to them the hyperbole at corresponding constant power. And so yeah, you can have an engine with a transmission, and you can generate the desired amount of power at partial throttle, and deliver it at different RPMs by the use of a transmission. Could be a continuously variable like a CVT transmission, or a manual transmission, multiple step transmission. And you'd like to maximize the specific fuel consumption. With automobiles, everybody knows the driver is responsible for actuating the throttle. But when you cruise the car and you put it on cruise control and you set it for 70 miles per hour, the high speeds on a highway, you would like to have the engine operating at best fuel specific fuel efficiency. So you're on this curve. Same amount of power can be associated with various specific levels of fuel consumption. So in this case, I would like to run my engine on highway at 25 for this particular engine at 2500 RPM. Okay, and if I do so, I'm running at the best fuel efficiency, and that's why overdrives have been introduced on automobiles. The early ones, they had only 3 speeds, and in order to move fast, you need to accelerate the engine. It was operating. So say the amount of power would be 1 given the rolling resistance and aerodynamic drag, but it's one thing if I run it at 4, let's say, maybe this will be too exaggerate, but could be at 3500 instead of 2500 with a significant effect upon the fuel efficiency. Okay, and these are important. Again, when you have transients driving in the city, accelerating, braking, but when cruising on highway, these are clear to define. So choosing the transmission and final drive such that I'm running at close to the best. Will be partial throttle. Yes, I'm close to the best specific fuel efficiency. It's how you save on fuel. Likewise, when you're to drive a stationary load like an electric generator, so you have backup generator, the large one driven by diesel engines, and you would like to have them operating at their best fuel efficiency, and you do studies like this one. Okay, so between engines and whatever you're driving, the wheels, road wheels, or could be you have pump jacks that are driven by engines out in the field. Some are driven by electric power, some are driven directly by diesel engines, or generators, or ships driven by piston engines. So in between, there are transmissions and bearings, and there are small amount, but they add up, or through multiplication. So there are losses between gears that mesh, and belts that flex, and bearings and all that. So you can estimate the loss or the total efficiency by multiplying. Say I have a gear pair in series with a V-belt. So I'm multiplying the efficiency of the V-belt, average or typical efficiency of the V-belt, with that of the gear reducer, single stage 98, and you get the corresponding. Of course, multiplying numbers that are less than 1 makes the total even smaller for the result. So I said 95 times so 0.95 times 0.98, it's 0.93 or 93.1 efficiency, having in series a one-stage gear reducer with a V-belt drive. Okay, so there's some solved problems, and there will be an assignment for you to look at we'll go over them to some extent. The first one here introduces the concept of operating point. So this is the torque speed curve of a design would be B 3-phase motor, and this is the fan torque. So you have the motor driving the fan, and the two curves intersect at a point, and this point you extract from the graph the RPM, and this will be the operating speed of the fan. All right. Now, if I have a too large fan, a too small motor, this curve would be somewhere low, and you'd have an intersection. So imagine this being steeper, or this being reduced in scale, and this staying the same. That is a smaller size motor. If I have the operating point left of the maximum torque, then this would be an unstable operating point, because slight increase in load could induce stalling. Plus, you want to run the motor near its rated speed, okay? Because we know that rated speed is chosen, and rated torque are chosen or correspond to the best efficiency of the motor. All right. So for best electricity consumption, you want the operating point to be near the rated torque, rated RPM for that motor. Problem 2 here is, let me take a break. Okay, I'm back. So this second problem is about single cylinder engine, and we have the power curve and a torque curve. Torque curve is the one that we'll be working with, and I actually did this using the graph from the manufacturer, the Briggs & Stratton engine, Intech. It used to be the allowed motor or engine rather for SE Baja competitions. And the torque curve, I extracted points from the graph, put them in Excel, and got this parabolic curve that's approximating the torque curve. And what else do we know? So other than the torque speed curve, we know the weight of the car and driver. We know the gear ratio in the first gear. It says neglect velocity in the transmission, although we could include that, no problem. We know the radius of the rear wheel. We want to calculate the maximum or the speed of the car. Will be full throttle. So these are full throttle curves. Maximum speed of the car 35 degrees, and then calculate the maximum incline the car can ride and at what speed. Okay, so similarly to this simple problem, we need to figure out what the load curve is, and we have the torque curve given by this equation. We need to of course do the analysis either at the crankshaft, so resistance to rolling into uphill movement, and so yeah, those have to be evaluated at the crankshaft to intersect the respective curve with the torque speed curve at the crankshaft. The alternative is to evaluate everything at the wheel shaft, the ground wheel shaft, and see how the torque at the motor shaft, the engine shaft, it's transformed through the transmission. So the way it is by correcting torque with the transmission ratio, correcting N with the transmission ratio. Torque goes up, N goes down. But the way we'll be doing it is to analyze and evaluate the operating point at the crankshaft. There's some information. So we have coefficient of rolling resistance, or there's rolling resistance. Here are some typical values. Rolling resistance is resistance to rolling the tires, they deform. Also the ground under deforms and comes back, but there's not 100% restoration or restitution of deformation energy, and that results in this rolling resistance. But we can work with it as if it were friction. Okay, so what I'm doing, I'm starting with a free body diagram of the Baja car on an incline. Okay, so I have the slope angle alpha. Okay, so this is not shown, but it's understood, and it's also the angle between the normal to the car floor and the direction of the weight. Okay, alpha. I have reaction forces front and rear, and I have rolling resistance. It could be shown as a force. The front axle, we're assuming the wheels are the same. You can have front wheels with a different coefficient of rolling resistance for the same road surface than for the rear. Okay, but essentially, if the wheels are the same, assume the same coefficient of rolling resistance, I'm just taking reaction of front, reaction of the rear, and multiply by coefficient of rolling resistance. I use here mu r, although here it's labeled RR. We take a break and change it to mu r. Okay, so I changed it. The same notation for coefficient of rolling resistance in table 5.1 and in the text of the problem. Okay, and then we're going to do free body diagram of the wheel. I haven't discussed the friction force. We're assuming that the friction force is not saturated, so we have enough friction, a good condition road. The driving wheels are not slipping. Okay, this force here is not going to be coefficient of friction times normal force to the rear axle. Okay, again, good conditions surface, I can deliver all the torque to the wheel with no limitation. Free body diagram of the wheel. Now it shows the normal, or could be the rear axle, entire rear axle. It's a two-dimensional model. So I have normal force, and I have a friction force. They're orthogonal. I have reaction to bearings. I care less about these. I care about the wheel torque, the one that's essentially creating the push force. Okay, so if there is no motion, how shall I put it? So essentially, I'm going to some moments about the axis of rotation A of the wheel, and this force, if you sum forces in along the incline, the x-axis, this force is going to overcome the rolling resistance, and the component of weight, the slope resistance component of the weight parallel with the x-axis will be W sine alpha. Okay. NF and NR plus NR would be W, the weight of the car, times cosine alpha. So with some forces in the x direction, I'm some moments about the A axis. All right, and these are simple equations. We then go to take the eliminate, that is, the friction force between these two equations, and then take the wheel torque and convert it into resisting torque at the crankshaft. Okay, so I'm having the friction force again substituted here in the second equation, and then I take the torque equation, the crankshaft, and set it equal to, again, intersecting two curves. So really, if I have this as an equation and this is a second equation, like torque versus RPM for this and torque versus RPM, their intersection, just setting the motor torque equal to the fan torque. again assuming that I have them available analytically. So that's what I'm doing here. I have the engine torque analytically, and I set it equal to the resisting torque evaluated at the crankshaft. So that's why I'm dividing by nu. If there's any efficiency involved, then that efficiency is going to multiply this part of the equation. Okay. So efficiency, the way I'm introducing it in the analysis, is by multiplying. I'm just making sure that I take that back. And sorry. So I hope you're paying attention. So I'm dividing by efficiency. I'm making the resisting torque greater than for the ideal case by dividing with the efficiency to account for that. Okay. So I'm moving everything to one side. This combines with C. I have a quadratic equation, A, B, and the new C. I solve the quadratic, and as you know, there are two solutions, and I'm retaining the one that makes sense. And which one makes sense? The one that corresponds to, I'm listing here, so this is the torque speed curve, and this is load curve, which is not function of RPM, and there are two intersecting points. This will be the answer. This other intersection corresponds to the unstable branch of the torque speed curve. If I'm here, any slight increase in resistance will lead to losing speed and stalling the motor. As I slow down, if I'm on this other point, slowing down increases the torque available, and I can overcome up to the maximum. So I can overcome any momentary increase in resistance. So this would be the stable branch of the torque speed curve. From the maximum torque to the left, it's the unstable branch. So you find the right the operating point as the right RPM solution to this quadratic, and then if you know the RPM of the crankshaft and you know the transmission ratio, you can find the RPM of the wheel. So I'm just dividing the RPM of the crankshaft with the transmission ratio, get the RPM of the wheel, and then I convert RPM of the wheel, knowing the wheel radius, into the so there will be tangential, assuming there's no slip in any way of the wheel on the road surface, and I'm calculating the corresponding speed in miles per hour, kilometers per hour, whatever. The second question is the problem is what's the so this was for 35 degrees. What's the maximum incline that the car can ride? There are two approaches to this problem. One is so the maximum slope it can drive would be, and at what speed would correspond to the maximum torque being delivered by the engine. And I can find the maximum from the equation of the an squared plus bn plus c. So I can find the maximum, take the derivative, set that derivative equals 0, so it'll be 2an plus b equals 0. You calculate n for the maximum is going to be negative b over 2a, and then and then take that n value and you plug it back in and you calculate the maximum torque. Okay, so take the derivative, set derivative equals 0, calculate the n. There will be the n at maximum power. Calculate the maximum power. I'm sorry, when I said power, I meant to say torque. So you calculate maximum torque by taking the derivative of the torque, finding the RPM that cancels the derivative, and plug it back in, calculate the maximum torque. And you also retain the RPM of the maximum torque. The RPM of the maximum torque is going to be, using the last of the equations, will be the speed on the maximum incline. What's the maximum incline now? You would have to go back to these early equations we have the wheel torque being the maximum torque times I, okay, and then you go back and so I have the maximum torque now from the torque speed curve, and I solve for F and plug it in here, and I get an equation with A times cosine plus B sine equals C. We solved that type of equations when we, if you remember, when we analyzed the 4-bar linkage. Wow, such an unexpected encounter. So 4-bar linkage equation and maximum slope of a vehicle like this, and then so yeah, you solve for alpha. You report the one that makes sense. A negative alpha, it's not a solution, and that'll be it. The other possibility is to look at the meaning of these two dual solutions. So as I'm increasing the slope of the incline, these 2 points will get closer to each other until they coincide. So maximum slope would correspond to these 2 solutions, N1 and N2, being coincident. So I can essentially take the discriminant of this quadratic and set it equals 0, and from there, so discriminant equals 0, I can calculate the maximum torque. Okay, so you know, I explained the first part with calculating maximum torque, and then the other approach with discriminant equals 0. It's detailed here, okay, and of course solution should be the same, and the same, we get the same equation, A cosine alpha B sine equals C type equation. I'm yet to type this part of the notes, but essentially this is it. You're going to have a problem assigned, and you need to go through these steps. So if instead of having the wheel in contact with the road surface, I have the wheel designed as a winch, and it's wrapping a cable that is anchored at the top of the slope, the problem is going to be exactly the same as the one that will be assigned to you as homework. Okay, there's another sample problem you may want to study it. I taught one semester of Intro to Automotive Engineering elective, and we went through this analysis. Rolling or rather the load curve is no longer a constant curve, but rather a curve other than linear, and it increases with speed because of the air drag. Okay, and analysis happens in the manual transmission in the 5th gear or the 4th gear, yeah, you may want to follow the steps. I'm not going to video. Sample questions and exercises for this chapter 5. There are several. You'll see a homework based on this, where we need to extract the maximum torque and the maximum power and the corresponding RPMs, and calculate a torque increase and also the speed ratio. And these are problems. This one is the one that I'm usually assigned. Could also be where you have, this is a crate that's moving, and instead of friction you have rolling resistance. Okay. The odd examples where we have possibly exam questions where we have the torque speed curve of an electric motor, and that drives directly or rather drives via a belt transmission, a cutter. And let's see, this one onion diagram. So it says the engine was the onion diagram, a consumption map onion diagram as shown, drives an electric generator, steady input power 32 kilowatt, and has to be run at 1800 RPM. So from consideration of maintaining that the desired frequency, so you have a backup generator, you want 60 hertz, based on the number of poles of the generator, you calculate the synchronous speed as 1800 RPM. So it'll be 4 poles. You go back to earlier, early in the chapter. And it says, what should be the transmission ratio between the motor crankshaft and the generator shaft for best fuel efficiency? So we have 32 kilowatt, and these are the constant power hyperbole, and we have 32 kilowatts. This is the 40 constant power lines, so 32 would probably be somewhere along. I could take this and copy it and paste it into Paint, and so let's use color or maybe the pencil. So I have 35, 32. Okay, so this could very well be the 32 constant power hyperbola, and according to this graph, I found the point. So they are nested curves, and looks like the minimum best specific fuel consumption would be at that location. Okay, so you draw this line, vertical line, and you read the RPM. So what's the RPM here? 15, 17, 50. I don't know. It's apparent that is maybe 1900 RPM. So you can calculate the transmission ratio now. The transmission ratio I as 1900 over the 1800 RPM of the, so slightly above 1, assuming that this was done at scale. It might be not too far off, although this is not quite at 32, so it would be a lower curve. Okay, so 19 over 18, transmission ratio of slightly over 1.06, 1.05. Okay, so that will be the if I use a belt. Of course, you would like that to be timing belt, not to lose any sync or speed or any slip. Okay. All right. So yeah, this is one, and then I have some for the earlier part of the notes, some questions. So main motor, universal, or the bench lathe, those in the machine shop, what kind of motors they used, in our machine shop, all the lathes that we have, they run 3-phase, asynchronous. What motor does an inkjet printer use to drive the pages is being printed? Definitely stepper motors. Servos are servo motors used in robotics because an expensive, low precise position can hold fixed position under load, have low stall torque. Allow precise position can hold fixed position under load. This is for the permanent DC motor here. So you want to find certain parameters. Let's go and see what it's required. Stall torque. Print screen. Paste. Copy, undo, paste. I'm gonna make this small. Okay. I know you can't see right of this line. It says curve. So what is the stall torque? So the stall torque is going to be the value that you're reading here. It's, what do we have? 250. This is, what do we have here? Need to figure out the divisions on the graph. Looks like it's 300 millinewton meters. Okay, so that's the stall torque. A stall current, you read it. The current axis, the second. So you move from here. That was supposed to be a line. Okay, so stall current would be this value. It gets close to 440 amps. You may not have a power supply capable of delivering this 40 amps. Okay, so you might have the like the rated current only maybe 15, not even. Well, how many amps would be if I'm assuming the maximum efficiency is for the rated current, then so say 20, 10, 7 amps. So you may have a power supply like batteries that are not able to deliver this maximum, the stall current. Or if they do attempt to, or as you stall the electric motor, the voltage will drop. Everybody knows when you crank the engine with the lights on at night of your car, the lights dim because the battery voltage drops as it drags a lot of current, the starter motor. Okay, so we have the stall current figured out, around 40 amps. The zero load RPM. Zero load RPM. You look at this curve. So it would be, this is the torque, the N curve, torque speed curve, and we have 10,000 RPM. Might be 8,000 RPM, like right here. Zero load. And then RPM for maximum efficiency. What do? You lower the line where it intersects the. Let me change color. So it intersects the N curve, and you read. Should be only here. So it's more like 8,000 RPM, whatever this number we said it is. So the RPM for maximum efficiency, you lower the maximum efficiency point, intersects the end curve, read to the right the corresponding efficient. What's the RPM for maximum power now? So for maximum power, you lower the line, and looks like there's somewhere here, maybe just coincidentally the two intersect. So it would be less than 5,000 RPM, maybe 4,500 RPM for maximum power. Okay, equation of a torque speed line. So we have the torque speed line. You know the stall torque. You know the maximum RPM. You write the equation of a line through 2 points. Equation of the torque current line, you do the same. It's going to be this one. It goes through 0 and it goes through the point. So here we have the stall torque, so say equation of torque current line, torque current. Okay, torque current. So we need, likewise, we need 2 points on the curve. So one will be 0, 0. The other one will be the right curve. The other one would be the stall torque and 0 speed. So I have, let me just back off a little bit. I hope I have the graphs labeled the way they should. Okay, so this is the current torque curve. Let me take a break. Okay, I'm back. Not that long break. So one curve is the torque speed curve, and we have 2 points on it. I'm going back a little bit. So we have the 0 RPM goes with the maximum torque, and 0 torque goes with the maximum RPM. That's one. And then we have the current versus torque curve. So we have 0 current go with 0 torque, and then we have the maximum current goes with maximum torque. So that will be the torque speed curve, or rather the torque current curve. What is asked here, G. Equation of the power torque parabola using chart data. So we have the equation, and we can fit, import this, or if you pay attention, yeah, you can see these numbers here. So you can read points on the parabola, or rather follow with the cursor in an assistant or yourself. You write down the pixel numbers here, and then you can convert from pixels on the figure to units of what do we have? We have power and of torque. If it's helpful, you can also flip and translate the image to where this origin is 0, 0. Why is that? Because in Paint, Y is positive down. So the y-axis is reversed in Paint. I've done this. I've done this also using AutoCAD. So yeah, that's one approach. You just extract points and use Excel, and you match a parabola through the points. The other one is to use the torque speed curve. So if you have the torque speed curve, then you know that, and this is mechanical power, by the way. This is mechanical power, not electrical power. So you can go back and forth between torque and power via omega, so or RPM. So I guess this was it. Yeah, you may have to do this for projects. So you have from manufacturer, you have the product specification, torque, speed curves, but they are on paper. Seldomly they are available as equations. So it's your job to derive the equations for the prime mover or engine or electric motor that you want to use. Show the constant power motor has a hyperbolic torque speed curve. We discussed this. Select all, paste. Alright. Constant power motor has a hyperbolic torque speed curve. Okay, so P equals constant, and you write this. And change font to maybe 14. Hey, what's wrong? So, or 16. And so I have power equals torque times omega equals constant. All right. And I could say from here now that torque equals power over omega. So power is a constant, and it goes of the form 1 over omega. Okay, so 1 over omega, or 1 over x, if you say, 1 over x equals f of x, and you plot this graph, you just get that nice hyperbola, and it doesn't intersect the axis. It's an asymptote. Okay. Double action hydraulic cylinder is powered from, I have these solved on paper. Maybe I should just scan the pages. So have a hydraulic cylinder, 80 psi hydraulic accumulator. So accumulator means this pressure is available constant. It doesn't drop with consumption. We have the bore diameter, rod diameter. What's the force can be overcome in both directions? Of course, it will be larger force that will overcome to the right, because I have the pressure applied on a larger surface. When I'm applying the force this way, I have to subtract the area of the rod. So you're always seeing applications, dual action hydraulic cylinders, like in excavators. The cylinder is oriented with this end up, because it's maximum force working against gravity. Okay, so you just take the pressure, multiply with the, for first case, pi diameter squared over 4 gets you the force. This other case, you subtract pi diameter, major diameter, or cylinder bore diameter squared over 4 minus pi, this lowercase d squared over 4 times pressure gets you the other force. It says find the end of the stroke velocity in both directions when a resisting force of 8,000 pounds is applied. A piston rod assembly weights together 8.5 pounds. This is the dynamics problem. So you have a resisting force, and you also have inertia, and you have a travel So you state Newton's second law, force equals mass times acceleration, and you want the acceleration, rather the velocity after 18 inches of travel. You state acceleration as derivative of v with respect to t. You change a variable from t to s. You get force equals what do we get here? So it'll be velocity over or times, well, like I said, I have it written. I could switch to Paint. I'm going to just post the solutions. It's a change of variables in order to be able to integrate with respect to s rather than t, time, and you integrate from 0 to 18 inches. It's classical dynamics problem. And then there's another one last problem. Says what's the air consumption. So let's take the screen first. Print screen, go to Paint, select all, paste, and select again. Okay, text of the problem, and refers to the air motor. The air motor. We had it here. Okay. So print screen again. And okay, and transparent selection. So it's neither 70 psig nor 90. It's in between. Find the air consumption. So when loaded with a 250 pound-foot of torque. Okay, so 250 pound-foot of torque will be this line, and I'm going to extend it all the way to the other side, or rather stop early. And then I'm trying to get this parabola. I'm switching to pencil, and I want to get, assuming that's a curve right in between for 80 psig. Okay, and I have the intersection point. Okay, and I lower this. Actually, I can draw a straight line now. Straight line, and then I draw again an in-between curve for 80 psig, and I have the intersection point, and I can read air consumption. Okay, so it appears to be so 400, 500, 600, 650 standard cubic feet per minute air consumption. All right, so I had to interpolate the consumption curves, or rather the available pressure curves, and went from torque to RPM, and then down here and this way. Okay, so I guess this will be it. Hope you learned, or definitely, but it was explicit enough, and there will be, as promised, a homework assignment. Thanks for watching. Have a good rest of the day.